So now when we want to do a double integral over a region D, we might do it using rectangular coordinates, x and y, or now we have the choice of doing it in polar coordinates. So we would substitute for x and y, and then we substitute for dA, and we get an extra factor of r. So it's important to take that out of this expression. The little area element dA is equal to r dr d theta. And your book has a little derivation as to why that ought to be so. So, for example, if we were going to integrate over this ring-shaped domain, okay, where we had r going between a and b, theta going between 0 and 2 pi, then we might be able to write down f r dr d theta, and as always the order is very important. So here we're integrating r first, and we go from the inside out, or we could go in the other order, r d theta dr. Theta goes from 0 to 2 pi, r goes from a to b. And we'd be integrating from the inside out. One thing that's interesting about writing it that way is that in this integral with respect to theta, r is considered to be constant, so we can actually take r through that integration sign. So we could also write this as r times the integral of f d theta dr. Okay, or if we have this teardrop-shaped region where r is cosine of 2 theta on the boundary, you have to do a little work to show that theta goes from minus pi over 4 to pi over 4, but it does. So then we would write this integral f r dr d theta, r going from 0 to the cosine of 2 pi, theta going from minus pi over 4 to pi over 4. In this case, it would not be so easy to reverse the order of r and theta, and it certainly would not be at all easy to do this in terms of x and y.